Okay, so this tutorial for Chemistry 3511 is going to focus on esters. These are common functional groups that we find in lipids as a biomolecular class. So this is a functional group that results from the reaction of a carboxylic acid and an alcohol under acidic conditions. And this specific reaction is called the Fischer esterification. We'll talk in a minute about why you can't use base catalyzed conditions or base promoted conditions, and we'll distinguish those to make esters out of a carboxylic acid and an alcohol. So what we're talking about is this general reaction here. We've got a carboxylic acid and alcohol, 1 mole of each, combining to form an ester and water. And remember, basically what we've got here is a carbon that has a double bond to an oxygen, a single bond to an OR group here. Okay. Now, this forward reaction will proceed at a much higher rate under the presence of an acid catalyst. So here I've just shown hydronium ion. This will not proceed in the presence of a base catalyst. Okay. Now the reverse reaction, where we're hydrolyzing this ester, we're adding water back across this ester linkage, is catalyzed by acid, and it's promoted by the presence of base. And again, we'll make the distinction about that when we show the mechanisms. Okay, so individual steps of the acid catalyzed formation of an ester. And of course the reverse of this whole process is just acid catalyzed ester hydrolysis. So we're starting off here with 1 mole of carboxylic acid, 1 mole of alcohol, and we're showing an acid here in the form of hydronium. Now this has to be present in a catalytic amount, otherwise it's going to cause us problems in a little bit. We have to have excess alcohol, and we'll talk about that. So given this set of circumstances, the first thing that's going to happen is we're going to protonate this most basic site, the carbonyl oxygen. Just like that we talked about when we're making hemiacetals or ketals and the like in carbohydrates. So that gives us our activated electrophile, right? So now our relatively weak nucleophile can attack this activated electrophile to form a first tetrahedral intermediate. Now the way it is, right, as it's shown, our protonated alcohol is by far the best leaving group. It's the weakest base. So if this tetrahedral intermediate collapses back down to a carbonyl, this is going to be the leaving group that gets kicked out. And that just heads us back in the same direction that we came. So that's not beneficial to us. We have to do something to make this a poorer leaving group and do something to make this a better leaving group, right? So we need to do a little proton shuffling. So what we want to do is deprotonate this alcohol group. Now we get another tetrahedral intermediate here. And we want to protonate the alcohol functional group, the hydroxy functional group to be more specific. So that now, if this tetrahedral intermediate collapses, this is the best leaving group, it's the weakest base, it's going to be lost. Okay? So now when this does collapse, we get a protonated ester here. And all we have to do now is grab this proton away, which we'll show here. And we get our ester, final ester. We get hydronium ion regenerated, and we get water as another product. So we started off with 1 mole of carboxylic acid. We started off with 1 mole of alcohol. We get 1 mole of ester, and we get 1 mole of water. We regenerate our acid catalyst. So this is a true catalyzed reaction. Remember, our catalyst has to speed up the reaction without being consumed itself. Okay? Now, okay, so again, I'm showing the entire reaction all in one step because some people need to see the kind of the big picture, whereas others need to focus in on the individual steps. So I'm trying to give you kind of both sides of that coin. So this is the entire acid catalyzed mechanism, ester formation mechanism, starting here, following it all the way down through, ending here. Now the hydrolysis, acid catalyzed hydrolysis mechanism is just starting here and working your way backwards. And you should sit down and make sure that you can do this mechanism in both directions. And you'll understand every step. Okay, so I got a little note down here that says no base catalyzed ester formation, and we'll talk about why. So when we were making hemiacetals or hemiketals, our strategy was going to be that under a given set of circumstances, say this is an aldehyde, right? Then the most likely thing that was going to happen is this base is going to grab the proton off this alcohol, activate the nucleophile, and then we get attack. But this carboxylic acid is not the same as an aldehyde, right? So we don't get this nice, neat little reaction. We get a different nice, neat little reaction, right? Given this set of reactants, the most likely thing to happen is this strong base is going to pull the proton off this weak acid, right? But it's still a stronger acid than the alcohol. So this is the electron pushing that's going to happen in this case. Is we're going to end up with a carboxylate, deprotonated carboxylic acid, water, and an alcohol. Now, up here, the whole goal, right, would be to have an activated nucleophile and some electrophile. Again, if this was an aldehyde, that would work out great, right? Got a weak nucleophile, strong nucleophile, and if this is an aldehyde, this would be an electrophile, relatively weak one. But now when we get down here and we've deprotonated our carboxylic acid, we have a nucleophile, and, oh yeah, a nucleophile. So that's a problem. No base catalyzed ester formation. Okay? Now, having said that, we can use base to promote the hydrolysis of an ester. And we say promoted because in this case, you consume 1 mole of base for every mole of ester that you cleave. So you need 1 mole of ester, 1 mole of hydroxide anion, going to give you 1 mole of carboxylate, and 1 mole of alcohol. And again, we'll talk about that as we go through. So here, again, we have a strong nucleophile, and we have a pretty good electrophile as well. This carbon now has not only the carbonyl carbon pulling electron density away from it, but this oxygen is also pulling electron density. So this is a pretty electron deficient site. Things are ready to go. Strong, strong, right? So we get a tetrahedral intermediate that's formed. Now, when this tetrahedral intermediate collapses, we can either break this bond or this bond. They're both pretty crummy leaving groups, but they're about equally crummy, right? So these are both pretty strong bases. And normally they're not good leaving groups, but they're competing against each other. Their pKs are about the same, so we could have either one lost as a leaving group. If we lose this OH minus down here, we're just going back where we started. Right? If we lose OR minus, then we're on our way. You know, we've committed to hydrolyzing that ester linkage. So here's showing the collapse of that tetrahedral intermediate to form a carboxylic acid and an alkoxide anion. Now, these aren't going to stay in this form because, again, this is a very strong base. This is a weak acid. They're going to want to do a proton transfer, right? So that's exactly what happens. And the final product that we get out of this base-promoted hydrolysis of an ester is a carboxylate and an alcohol, okay, which is different than the acid-catalyzed situation where we got a carboxylic acid and an alcohol and we regenerated our hydronium ion. Okay, so work through these mechanisms, make sure you understand them. Based on what we learned in the carbohydrates unit about acetal, ketal, hemiacetal, hemiketal formation, and hydrolysis, this should be relatively easy for you to kind of see how this fits together. One more time, this is the entire base-promoted hydrolysis of an ester mechanism. Again, if that helps you kind of visualize what's going on in combination or standalone from the individual slides, then I hope one of these methods works out for you.